Okay, good morning. Today was an extra class, if you remember, uh, because of the Wednesday holiday. And it is, I think I got it right, but I don't find anybody. So I'm going to record it for all of you. So we have to change the way of doing this class. I wanted to pursue the constant pressure, going beyond the constant pressure filtration problem. But let us turn things around its head a bit. We can learn a lot, and there are so many extensions, even of the constant pressure part. So why don't you try some questions? And I will indicate what the concepts are and what the pitfalls are. And so take this down. You have to filter a slurry at constant pressure. At constant pressure, so it's the same case as earlier, through a filter medium whose resistance you can take to be negligible. In other words, filter medium Rm, R medium, or VE is 0. The following laboratory data is given. Weight of crystals 62 grams. Pressure of filtration delta P 1 atmosphere. Filter diameter. So this is like a circular filter paper, because this is just the batch test data, so you're using a filter of area whose diameter is given. Filter diameter 5.08 centimeters. Cake volume 253 centimeter cubed. Filtration time 163 minutes. The cake can be taken to be incompressible. So exactly the case I taught you last time. So this is the lab data. Now what you are asked is to actually go to a process, actual process with a plate and frame press and design it. So on the basis of the above lab test, predict the number of plates and frames. Predict the number of plates and frame needed for a plate and frame press. Needed for a plate and frame press, that is to filter 1,000-fold higher throughput than the above lab test. The dimensions of the plate and frame is given as 30 centimeters. No, wait a minute, just a minute. It says 1 foot by 1 foot by 2.54 centimeters. So the cross-sectional area is 30 inch by 30 inch. So 1 foot by 1 foot, you have to convert that to centimeters. And the thickness is 2.54 centimeters. So you are asked to estimate the time to filter a 1,000-fold higher, that is 63 kilogram batch. Okay. And there is a second part to it. If the feed pump delivers 2/3 of an atmosphere. The feed pump delivers 2/3 of an atmosphere. And the filtrate from the press has to be pumped up or raised against an equivalent of a hydrostatic head of 15 feet. In other words, you have to also pump this liquid up against a hydrostatic head of length 15 feet. Find the time to filter the 1000-fold higher batch of the system slurry. Okay, so this is the question, and let us try and learn by trying to solve this question, and we can discuss a number of attendant issues since there seems to be no attendance today. For instance, to solve this, you have to figure out what is the area capital A that you should use in the general filtration equation that I gave you last time, that I derived from first principles actually. I hinted that it's not just the geometrical area. So what is it then? If it is not the geometrical area, cross-sectional area, I mean. So that is one thing you have to settle. Then here, the filter medium resistance is taken 0 also. It's in some way, we don't have to plot or linearize the system. So the time of filtration will just follow the quadratic in the volume. The expression, the first term of that expression, and the product term of VE capital V is negligible, right? So that sort of just simplifies the problem. Though in a real system, as I said, we need to actually find capital V, but then that will make the problem unnecessarily long. Okay, so this is the first question. Now the number of extensions you can do even with the existing filtration theory that I have derived is so many that I'm just thinking now. Actually today I wanted to cover the non-delta P constant cases, but okay, let us change things and say that it's not delta P is still constant. We are still doing the same problem, but there are just so many extensions we can do. So after this problem that I dictated is solved and I interpreted it for you, and it has 2 parts, so it requires some careful study. Yeah, for instance, so in the above problem and the case we covered for the delta P constant filtration assumes incompressible cake. For biological system, that's not a great example. It works much better for purely chemical systems. So suppose now I would stipulate, so this can be taken as question 2, you have to think on it. It's a more conceptual question, not a numerical one like the previous question where you will get an actual quantitative answer. Suppose I were to stipulate that the cake is compressible, then of course I have to give you some constitutive equation that the filter cake follows as it accumulates and as the delta P changes, because the thing is, we simplified the situation by assuming that whatever be the delta P pressure that you impose, alpha does not change, as I said, for biomass and other systems. This is not really a good approximation. So now I'm just thinking that very common constitutive law that you can take, relationship that you can assume, is a power law type of expression of specific cake resistance alpha on the delta P. So suppose alpha is a function of delta P and it is given by some alpha naught, which is a constant, times the pressure drop delta P to the power S. Okay, so assume that alpha is equal to alpha naught delta P to the power S. Now this exponent S can have values between 0 and 1. So 0 is less than small s is less than 1. Of course, if s is 0, then we have the incompressible cake limit that we have already discussed and solved and derived the general filtration equation. But like for the experiments that we have run with Baker's yeast, I mean, alpha is somewhere in between. It's something of the order of 0.3, 0.4, 0.5, depending on the source, depending on the system. So in general, it will is somewhere in between 0 and 1. But whatever, recast now the equation that we derived such that it is valid for a non-compressible cake. Could be another extension. I'm thinking what other. In some way, through the first question that I dictated, recorded, we have also discussed this little bit of an issue of the scaling up, because once we have to design the press based on some small lab data, which is a circular filter in this case, by the way, which also obeys the same filtration equation. Essentially, we have to scale up the process 1,000 times. So from 63 grams, we have to go through 63,000 grams, right? So for that scaling up process, when we design the press, means you'll have to tell how many plates, how many frames, and you have to give sufficient filtration area. You can't give too little, otherwise you can't process the higher throughput batch. And obviously you don't want to give too much, it will just be unnecessary volume. So what is that design of the scaled up press? So some way it gives us some insight into scale up, another thing which we haven't had adequate time to do in our course. But as I said, it's something that I've made a detailed study of, but we may not be able to reach there. So that's the third point to discuss. And then now that we are anyway here, and what I actually wanted to cover, why can't we actually put that as a question? Okay, at least part of it, and I can discuss it next time on Wednesday, next Wednesday. How to frame it? I mean, earlier we set up the problem of filtration taking the pressure drop delta P to be constant. But as I told you, as the cake accumulates, the dV by d theta in our equation, the rate of filtration, starts declining with time. So beyond a certain time of operation, this renders the operation very inefficient. So question 4 could be, suppose I ask you to operate this press at constant rate of filtration at constant filtrate rate. What will the filtration equations look like? Then another question could be, once you derive this, can you also have a slope and intercept form by which the specific cake resistance, I'm assuming now, let us say an incompressible cake for the moment, but it can be, that can be extended to compressible systems. So assuming an incompressible cake, what will the parameters of the system be, and how will you determine them? How can alpha be found? How can V subscript E be found? The effective resistance VE, or rather the resistance which gives you, I mean, rather the volume of filtrate which models the effective resistance or the fixed resistance of the system. That's what we said, interpreted V subscript E to be. Okay, so I think you can think on all of these and work them out. And next Wednesday, what I suggest is maybe question number 1, your 4 days. Why don't you submit it to me? Yeah. Okay, and then we can move on to the other case, and I'll try to wind up this whole topic. So let us see some initiative from you guys. And maybe today you all forgot about the class, but I thought there was a class, I guess, because of that Ambedkar Jayanti holiday. Okay. Anyway, there are a number of things for you to do, but I just want you nonetheless to just try out the first question. And each one has to definitely tell me on Wednesday. All right. This way, you will learn something because you actually do it, and we can learn a lot by trying these things out. And then if some difficulties arise, they can be discussed, right? Okay, it's an actual applied question that I have given you. So please do it. And I should evaluate you on it. All right. All right. Okay.